In this video, we are going to look at some of the challenges that we can encounter when we're measuring the heat given off by a reaction. And we'll also talk about how we can counter those challenges and work with them. So first of all, let's start with measuring work. Now, measuring work is very difficult. Recall that when we are measuring the total energy change during a process or a chemical reaction, we need to include both the change in heat and the change in work. And also remember that the change in work is calculated by taking negative external pressure times the change in volume. Now, measuring the change in volume is pretty simple, but measuring the change in external pressure can be really difficult. So how can we just avoid this calculation? We want to make work equal to 0. As long as the volume isn't changing, then work can equal 0. So if we do a reaction in a container where the volume isn't changing, that makes our work calculation really simple. And this is that container. It's called a bomb calorimeter, and it's a reaction vessel that has constant volume. And it's kind of a complicated looking thing here, but it's a device used to measure the energy change of mostly combustion reactions. It's a sealed container, it doesn't change in volume, and it forces all the energy to be released in the form of heat. So we have a little place for a little sample. If we're combusting it, we have some oxygen in that environment where the sample can burn. We have a thermometer surrounded by water so the water can heat up, and a stirrer so that the water stays mixed. So bomb calorimeters are not the most easy pieces of equipment to work with. You need very specific components, and it really only measures really well most just combustion reactions. So rather than worrying about having a measurement at constant volume, let's take a look at what we can do if we have measurements at constant pressure. Now, most of the time, we don't care how much work is being done. We don't care if there's a change in pressure or a change in volume. What we're really interested in is a change of heat. So in constant pressure conditions, there's a thermodynamic quantity called enthalpy, and it's designated by a delta H change in enthalpy, and it represents just the heat during a chemical reaction, just the heat change during a chemical reaction. So delta H is equal to Q under constant pressure conditions. Now, here is why we need constant pressure conditions. The actual definition of enthalpy and the actual formula for calculating enthalpy is delta H is equal to delta E plus the pressure times the change in volume. So the quantity of the pressure times the change in volume. Now, we've seen this pressure times change in volume thing before. We saw it when we talked about the equation for calculating work. So what if we take this delta E and we solve for what we're used to solving for? Q, delta E is equal to Q, the amount of heat change, plus the amount of work being done, or the amount of work that the system is doing. So delta E is equal to Q times W. This should be a review formula. Now let's solve for W, or let's find an equation for W, work. Work is equal to the negative amount of external pressure times the change in volume. What we can do is we can take these different formulas, these different equations, and put them all together. Now if we put them together, we get delta H is equal to Q plus, now instead of writing W, I'm going to sub in negative P delta V, plus, if we continue on with the original H formula, we get P delta V. Well, what we can do here now is we have a negative P delta V and a positive P delta V. So if we have that negative and positive, we can cancel those out. And remember, in constant pressure conditions, we can cancel those out. And then what we end up with is delta H is equal to Q. And the little sub P just as a reminder that this is a constant pressure condition. A constant pressure condition would be an open air experiment. So if you do something in a beaker, that's an open air constant pressure device. So you're able to use these values. Now let's do a little bit of calculation and kind of look at what some numbers might look like in a chemical reaction. So the change in enthalpy during a chemical reaction is called the enthalpy of reaction, and it's noted by delta H Rxn usually to show that a reaction is taking place, not just a process or a physical change, but an actual chemical reaction is taking place. Now if you look at this reaction, this is the combustion of propane, and for this reaction, the delta H Rxn, or the enthalpy of reaction, is negative 2044 kilojoules. So what that means is that when I have this exact reaction going, so 1 mole of C3H8 and reacting with 5 moles of O2 to give 3 moles of carbon dioxide and 4 moles of water, this will release, hence the negative sign here, this will release 2044 kilojoules. Now whenever heat is released in a chemical reaction, the enthalpy is negative, and we have an exothermic reaction. Whenever heat is absorbed in a chemical reaction, the reaction will feel cold because it's absorbing the heat from your hands. So whenever heat is absorbed, the delta H will be positive and the reaction will be endothermic. So we have an endothermic reaction if heat is absorbed during the process of the reaction. But in this reaction, heat is released, so this would feel hot. Burning propane releases heat and light and all kinds of energy, so we can, warm our hands over the combustion of propane. And 1 mole of propane burning will release 2044 kilojoules of heat. So what we can do with this is we can make a conversion factor with this amount of energy and this amount of moles. So my conversion factor would look something like this: 1 mole of propane over negative 2044 kilojoules. Being that it's releasing, it should be a negative amount of energy. So this is just a conversion factor that I can use to solve problems. So here's a practice problem. If ammonia reacts with oxygen according to this equation, it will release a certain amount of heat. So we have 4 moles of ammonia reacting with 5 moles of oxygen to create 4 moles of nitrogen monoxide and 6 moles of water. And that releases 906 kilojoules of heat. So it's an exothermic reaction. It's a negative enthalpy of reaction. But it's asking how much heat is released when 155 grams of ammonia reacts. Remember, in a laboratory setting, we don't have a tool to measure moles, but we do have balances all over the place, so we can measure the amount of ammonia using a balance. So in our balance, we would measure out a mass of 155 grams, or we can use 155 grams. That's our given quantity. The next thing I want to do is use a conversion factor. I abbreviate conversion factor with CF. Now my conversion factor is going to relate the number of moles with the amount of grams. So I want to cancel out grams and turn it into moles. And I know that 1 mole of ammonia is equal to 17 grams of ammonia. And I use the periodic table to determine this. Nitrogen is 14 and 3 hydrogens add up to 17 grams, or about 17 grams. The next conversion factor that I'm going to use will relate moles to enthalpy. Now, according to this equation, we have 4 moles of ammonia here, and that causes a release when it's reacted of 906 kilojoules. So I need to make sure that I include the 4 moles of ammonia on there, because that indicates the quantity that goes with the 906. And if I calculate all this out, I get a negative 2070 kilojoules. That should be a negative on there. So a negative 2070 kilojoules will be the amount of heat released when this reaction takes place. Let's take a look at another problem. We have the reaction for the combustion of butane, C4H10. When 1 mole of butane combusts, it releases 2,658 kilojoules of heat. What mass of butane is necessary to produce 1,500 kilojoules of heat? And then another question says, how much CO2 is produced when 1,500 kilojoules of heat is released? So what I'm going to do first is write out this equation. So I have a combustion reaction. Butane is C4H10, and during a combustion reaction, we are adding oxygen and getting carbon dioxide and water as products. I'm going to balance this. So 2 moles of butane will react with 13 moles of oxygen to create 8 moles of carbon dioxide and 10 moles of water. So I have my balanced equation. Now what I'm given in this reaction is that my starting number needs to be 1,500 kilojoules of heat. And what I'm solving for is the mass that is required to produce this amount of heat. So I'm going to start with what I'm given. I'm given 1,500 kilojoules. So I start with what I'm given. I'm going to label that here. And I have 1,500 kilojoules, and it's being released. So I'm going to keep that negative, just to remind myself that that is released. That's energy released. That should be a negative. And now the next thing I want to do is I want to cancel out kilojoules, and I want to turn it into moles. I know the relationship between kilojoules and moles. When 1 mole of butane combusts, so 1 mole is equivalent to 2,658 kilojoules. So when 1 mole of butane combusts, it will release 2,658 kilojoules. So I'm going to keep that negative as well because it's releasing that amount of energy. But my question isn't asking for moles. It's asking for grams. So I need to do one more conversion. I need to convert moles of C4H10 to grams of C4H10. And to do this, I need to use the periodic table. 1 mole of C4H10 has a mass of 58 grams. That's the molar mass of butane. And I use the periodic table to find that out. So I'm going to do this whole calculation, and 2 negatives multiplied together creates a positive number, which is good. This is what I want because a mass shouldn't be negative. We're asked to find a mass. So I get 32.7 grams of butane, so C4H10, 32.7 grams of C4H10. But my problem isn't done. I still have one more question that I need to answer, and that is how much CO2 is produced when 1,500 kilojoules of heat is released. And there's actually a few different ways you can solve this. So if you look at this question and think to yourself, well, I probably solve it a different way, that's totally acceptable. You could start with 32.7 grams of butane and end with grams of carbon dioxide. That's a perfectly acceptable way to solve this problem. But because we have been practicing with heat and learning about how to use heat and the conversion factors that go with heat, I'm going to solve this problem using a conversion factor that involves energy. So I start with 1,500 kilojoules being released, so that's a negative number. And then what I'm going to do is multiply by 1 mole of C4H10 over negative 2,658 kilojoules because those are equivalent values. 1 mole of butane releases 2,658 kilojoules, so that number should be negative. And now I'm going to go and do my mole ratio in the balanced equation. So 2 moles of C4H10 will create 8 moles of carbon dioxide. Remember, carbon dioxide is what we're trying to solve for. That's the mass that we're trying to solve for, that we're being asked about. But then I'm not asked to stop there. I need to continue this further one step to solve for grams. So then I use the molar mass on the periodic table. 1 mole of CO2 will have a mass of 44 grams of CO2. And then I calculate all this out and I get 99.3 grams of CO2. Remember, you can use the ratios in your balanced equation as conversion factors relating your balanced equation to the amount of energy produced in that reaction or the amount of energy absorbed in that reaction.